Example 3.4.4, Part A, prove that x plus 2 is a factor of p of x, and factorize p of x completely. Now, of course, this is not trigonometry, this is revision from factor theorem and remainder theorem. So Part A, prove that x plus 2 is a factor. Well, we're going to work out p of negative 2, and if that gives us 0, that proves that x plus 2 is a factor. So don't just write equals 0, because then there's no evidence. So let's show it being substituted in. And that's going to be minus 16, take away 28, plus 34, plus 10. If you add the positive numbers together, you get 44. If you add the negative numbers together, you get minus 44. So yep, that does equal 0. Now we need a little tiny conclusion. Therefore, x plus 2 is a factor. You will lose a mark if you don't put this little conclusion. Very important. Now it's easy to think that's it, part A done, move on to part B, but remember there was two things to do in part A. Factorize it completely was the second job. Now it's up to you how you do this. There's various ways. You could use long division, you could use the grid method. I'm just going to do it by inspection. So I know x plus 2 is definitely a factor. We've been told that. Now I'm going to work out term by term what the remaining quadratic would be. Right, I'm going to do this by inspection. Looking at my 2x cubed, and see this needs to be 2x squared, because 2x squared times x gives me 2x cubed. I now have 4x squared here, but I want to get down to minus 7. So I'm at positive 4 at the moment, and I want to get down to minus 7. So if I take off 11x squared, which will come from multiplying those two together. So 4x squared, take away 11x squared, gives me my minus 7x squared. I'm constantly checking that I'm getting the right terms. Now that gives me minus 22. Oh, I've put a squared on there, I shouldn't have. That gives me minus 22x. I need to increase that up to minus 17x. So if I add 5 here, and then double check, so 5x from there, minus 22x from there, yep, minus 17x. And then I've got the benefit of a little check at the end. 2 times 5, both positive, gives me positive 10. That's a good sign. That means we probably factorized it correctly. It is possible that you've fluked it and got the right constant term but messed it up elsewhere. However, if we didn't get positive 10, we'd know we'd definitely done something wrong. Now there's no clue in the question as to how far this factorizes. It just says factorize it completely, and this might be it. This quadratic might not factorize. So in a question like this, don't always expect the quadratic to factorize. It might not. But in this case, we do get a quadratic that factorizes. And by expanding that out, we can see that gives you the quadratic from above. So therefore we can't go any further. That is it, factorized completely. Now in part B, hence is the first word in the question, so we're going to be better off if we use what we've just done. It does say or otherwise, so there'll be other ways to do this, but it's best to do the work we've just used in part A. Solve this equation, giving all solutions in degrees to the nearest half a degree. That's unusual, but we've got to follow that. So nearest half a degree between 0 and 360. First of all, check, is it the exact same cubic? So we've got 2, and then minus 7, then minus 17, and then 10. So yep, we do have the exact same cubic. Of course, this time it equals 0. We're actually solving where does it equal 0. Instead of x, we've got cosec theta. So I'm going to let x equal cosec theta. That's the link between part A and part B. And by looking at part A, we have the factorized version of this cubic. Remember, in part A, this cubic didn't equal 0, but now it does. So where would it equal 0? Which values of x would make each of these three brackets equal to 0? Well, we can see we've got minus 2, a half, and 5. Those were the values of x from part A that would have made the brackets equal to 0, and therefore the whole cubic equal to 0. So they equal cosec theta. Cosec theta is 1 over sine theta, so we can come to the conclusion that sine theta must be either minus a half, or 2, or 1/5. That's because cosec theta, by definition, is 1 over sine theta. If you remember, sine theta has a maximum value of 1 and a minimum value of minus 1, so it can't equal 2, so we won't get any solutions from that possibility. But it can equal minus a half, and it can equal 1/5. Okay, I've drawn a quick sketch of, I've labelled it cosec theta, it isn't, it's sine theta. That's a quick sketch of sine theta between 0 and 360, that's what the question said, 0 to 360. Notice we're in degrees as well, so calculator, double check that you've got D on your screen. If you don't, then go into shift and then setup, number 2, angle unit, and put it in degrees mode. On my rough sketch, I've drawn the graphs of y equals a fifth and y equals minus a half. So I can see there are going to be 4 solutions here. So it'll be 1, 2, 3, 4 solutions. Right, let's get them. Inverse sine of a fifth, I'm going to do the first two. The two I can see on the graph that are between 0 and 180 first. So inverse sine of 1/5, I get 11.5 degrees. This angle is not going to be multiplied at all, so I'm okay to round it to the nearest half a degree here. So that one there is 11.5 degrees. I'm just going to move the 180. So that means the other one is going to be 180 minus that. Because on the graph, if I do this in purple, from the y-axis to there, if you can see that small little purple arrow, that's 11.5 degrees. By the symmetry of the graph, from 180 to the left is also going to be 11.5 degrees. So we've got theta is 11.5 degrees. Also 180 minus that. So that's the two answers to sine theta equals 1/5. Now sine theta equals minus a half. Well, if we put inverse sine of minus a half in the calculator, it gives us a negative angle, which is fine, that's correct. We've just got to know how to deal with that. So imagine the graph was continued into the negative x values, or negative theta values. So it's given us this one here, minus 30 over there. So if we add a whole period onto that, so 360 degrees is the period of sine theta. It's also the period of cos theta as well. So if we add a whole 360 onto that, it takes us to this one. The same point on the graph, just a whole period later on. So this will be 330. And I can see that is 30 degrees to the left of where it crosses the axis. So by symmetry, the next one's going to be 30 degrees to the right of where it crosses an axis. So we've also got 210 degrees and 330 degrees. If you're ever not 100% sure, then all you can do, well, you can just grab a calculator, do sine of 210 degrees. Does that give me minus a half? Yep, so we know 210 is definitely correct. Do the same thing with 330. Yep, so then you know these two angles are definitely correct. You can do the same with the others. So I'm just going to store that 11.5 under x. So x at the moment is 11.5. So sine of x should give me, oh, what have I done wrong? Let's bring that back. Okay, I think I stored the wrong number. So store 11.5 under x. Let's just check, go to recall. Yep, x is 11.5. So sine x should give me 1/5, and it does. So let's check this other one. Sine of 180 minus that. And there we go. So we can be completely confident that all four answers are correct. So let's finish it off. Can't leave our answer like that. So we've got 11.5 degrees and 168.5 degrees. So they were all ready to the nearest half degree. Remember the question? It was a bit unusual. It said to the nearest half a degree. So they were all ready to that accuracy anyway. The next two, we don't need to round them because they are exact. Exactly 210 and exactly 230 degrees. And the graph told us there was only going to be 4 solutions. And there we go, we've got them all.